Saxon Advanced Mathematics, Lesson 19. We have a hearty algebra review. A couple different topics. I'm pretty sure it's all algebra. There's no geometry. That's next lesson. It's probably going to be kind of long. There's a lot to cover, so bear with me. I'll try to not have my camera die or chop this into bits. Remember that when we're solving systems of nonlinear equations, we're basically using the same strategy as we always use for systems of equations, right? We're trying to use substitution or elimination to find a value for x and y that will make them both come true. The difference is that the equations don't necessarily look a lot alike. In this example, John tells us that this one is a circle and this one is a line. That's why we have squares in that one. And we haven't spent a lot of time graphing circles, so you wouldn't be expected to know that, but I'm telling you. Okay, so we have to figure out what the heck we're gonna do about it. It sometimes helps to visualize it a little bit. Usually a circle and a line are gonna intersect like this, and we're gonna have two sets of x and y to solve. Okay, so what we're going to do is we're going to use substitution. We can't eliminate because the shapes of our equations are so different, right? We could rearrange, we could put the x first and then the y, we could make it minus x plus y, but still we have squares up here, that's not going to eliminate. So we're going to substitute, right? So what we're going to do is we're going to, let's call this one A and this one B. Here's our strategy. We're going to take B. We're going to kick one or the other sides to the other side of the equation, and then we're going to square both sides. And let's be honest, let's just choose y, right? Because it'll be easier. We'll take y and we'll let that equal x plus 1, right? We'll bump the x over. Then we'll square both sides. So we'll get y squared equals, can you square binomials in your head? I hope so. X squared plus 2x plus 1. And I don't need parentheses around that. I just lost my mind a little bit, okay? If you need to write these out and square them this way, that's absolutely fine. Just do the dance to simplify, all right? No shame in, there's no shame in doing a hand calculation. Zero shame in that. Now we have a value for y squared that we can plug into our equation A, right? We turned B into a beast that is equal to y squared. Now we can plug it in here. So this was B that we were fooling around with. Now we're taking A and we're saying x squared plus, and now I know why I wanted that on there, right? X squared plus 2x plus 1, that's our y squared, equals 9. Okay, so we've substituted it in. Now we're ready to start the long, laborious task of simplifying. All right, these two can go together. So I have 2x squared, and let's subtract the 9 from both sides, plus 2x, and that would be minus 8 equals 0, right? 1 minus 9, and then those cancel. Okay, these are all even numbers, so let's divide everything by 2. You can do this. It won't make the world go crazy that you're dividing by 2. I mean, it doesn't blow up the kingdom because the zero's in the top. When I first started doing this in algebra, I always thought, it doesn't seem right. It seems like we're ruining something, but it's fine. So then we get x squared plus x minus 4 equals 0. we have to factor this. Can we just do it by inspection? Can we think of two numbers that multiply to 4 and multiply to -4 and add to +1? No, we can't. Trust me, when you'll see the answer, you'll go, yeah, that makes sense. Okay, I'm copying over. We're gonna have to get the dragon out of its cave and let it breathe some fire on this monster. X squared plus x minus 4 equals 0. So we drag out the man-eating dragon, aka quadratic formula. We remember it's x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Remember when we took the quadratic equation in standard form with a, b, and c, and we solved it to get this? We did completing the square to get to this. That was a fun time, wasn't it? Oh my gosh, that's one of my favorite lessons. I mean, that's like choosing a favorite child, right? I love them all. All right, our value for a is 1. Our value for b is 1. Our value for c is -4. Somehow that just makes me feel like this should be easy, but let's see. X equals, ready? We gotta bucket this. I recently learned that one of my very obedient and hardworking students does not use buckets. Her mom ratted her out to me. And I said to her, girl, if you can get the problems right without using buckets, more power to you. You are playing with fire and it's not worth it. You're just better off using the buckets, especially when, as you've heard me say, if the formula has negative signs in it and the values have negative signs, you're almost guaranteed to screw it up. It's just a matter of time. Okay, let's plug in. B is 1, A is 1, C is -4. Okay. Turning pages of other things as we go. All right, and remember, this is just a little review. The standard form helps us to remember which is A, which is B, and which is C, right? So that's how I made the jump from here to here. Okay, let's simplify. Let's do this. This is 1 plus 16, right? The two minuses make a plus. 4 times 4 times 1 is 16. All right, so that I can simplify as x equals -1 plus or minus the square root of 17, whoops, over 2. I was all excited about this. That's why I did this. Okay. Now, I want to separate these into two separate fractions rather than show them as one. But I can do that later. X equals -1 plus square root of 17, and they're each over 2, or x equals -1/2 minus square root of 17 over 2, right? Now what we have to do, this is our solution to the quadratic equation. This is me writing them in separate form, right? The plus and the minus, there's the plus and there's the minus. Now what we have to do is take one of our original equations and put this value for x in and then solve for y so that we have both pairs of points. Let's go back to our original equations. I would like to use this one, y equals x plus 1, right? Which was this rearranged one step. Y equals x plus 1 will work really nicely for us. Puffy cloud it, because we're going to need that. Because x is all ready to go. So I'll say y equals -1/2 plus square root of 17 over 2, that's x, plus 1 is 2 over 2. All right, I gave it a denominator. I'll be able to combine these two. Now y equals +1/2 plus square root of 17 over 2. Right, when I add -1/2 and plus 2 over 2, I get plus 1/2. That follows along. Now I'll do this side. I plug into my y equation. Y equals x. X is minus 1/2 minus square root of 17 over 2. Plus 1, I'll add it as 2 over 2. So y equals positive 1/2. Minus 1/2 plus 2 over 2 minus square root of 17 over 2. We're almost there. The last step which I kind of want to do on a separate piece of paper. I'll do it on this so that you can see. To write the final answer, I write the x value minus 1/2 plus square root of 17 over 2. I make a comma, and then I put the y value that goes with it. Positive 1/2 plus square root of 17 over 2. That's one pair of points where our circle and our line intersect. Okay, that's this side. The other side is minus 1/2 minus square root of 17 over 2. That's the x value, and that's associated with this one. Positive 1/2 minus square root of 17 over 2. That's a minus. I accidentally started writing a plus. All right, so these are our 2 points. I'm just double checking in the book to make sure I did it right. Yes and yes. This is the final way we want to format our answer. And if I would have had room, I would have written it here, but I didn't want to turn the page because we want to see everything, all right? So the x and the y that goes with it, the x and the y that goes with it. Yay! Turning page. John says, if 1 was fun, then just imagine how great 2 is going to be. And he gives us another chance. Ready? This is example 19.2. Here we go. And he tells us circle, hyperbola. A circle is like this, and the hyperbola are like the basketball marks. So we're likely to have 4 points of intersection on this one. Ooh la la, right? And again, I'm not graphing this exactly. I'm just saying when you have a circle and a hyperbola, this is the classic way that they relate to each other. Then we have an A and B. Now, in this pair of nonlinear equations, we have a little more option because they both follow the same form. They both have an x squared and a y squared. So that means that we could still substitute, but I notice this. I look down the columns and I go, dude, that's ready to go. Let's just add them and start solving. So let's do it. 3x squared, that cancels, equals 3. Wait a minute. John, could it be? X squared equals 1. So that means x equals plus or minus 1. You with me? That's very exciting. That means that we're ready to start our 2 columns, right? Here's what happens if x equals 1. Here's what happens if x equals negative 1. And then I do my separate calculations to find the y's in each possibility. All right, we could use either one of these equations, or we could play around with it. I'd like to take this one and make it, here, let me just come and write down here. I'd like to make it y squared equals 9 minus x squared, right? I'll move the x squared over, and then I'll take the square root of both sides. So I'll get y equals the square root of 9 minus x squared. That allows me, that's not necessary, but it allows me to do all the algebra up front, and now when I'm actually working with the numbers, I don't have to do as much. So y equals the square root of 9 minus 1 squared. Y equals the square root of 1 squared is 1, so it's 8, right? So, and it should be plus or minus. Y equals plus or minus square root of 8. I can simplify that. Y equals plus or minus 2 times the square root of 2. So here come my 2 points. 1 times 2 square root of 2. 1 and minus 2 square root of 2, right? Because I've got 2 here. This is how I'm getting 4 points, right? And now I'll do the same thing with the minus 1. Y equals the square root of 9 minus 1 squared, because x is minus 1 over here. But once we square it, it's 1. It's exactly the same as before. Y equals plus or minus the square root of 9 minus 1 is 8. So that means y equals plus or minus 2 times the square root of 2. And then we can write these two values. It's minus 1 plus 2 square root of 2 and minus 1 minus 2 square root of 2. So here are our 4 points. And we usually do get this really nice pattern of pluses and minuses because, as John shows us, if our circle is centered on the origin, then we're going to get this really symmetric pairing of points like this. They'll be mirrored across the different. It's all even and perfect is what I'm trying to say, right? If that goes right into the middle of the circle, then it makes sense that the points will be the same numbers, just plus and minus of them. Okay, yay, we got that right. All right, that's 91.2. Oh, there's one more. Oh my gosh, you guys, we hit the jackpot today. We're so lucky. Example 19.3. Another system. This one says x times y equals minus 4 and y equals a and b. They're a system. We have the parentheses to prove it. This one is a hyperbola. And this one is a line. John tells us that. Hyperbola looks like this-ish. And so we're talking about something that goes like that. And it intersects at 2 points, typically, is what we would expect to see here. Now, again, there's multiple ways we can do this, but the easiest way I can see is to substitute. Let's take this and we'll plug this expression in. So we'll substitute B into A. So we'll do x times minus x minus 2, right? Because that's equal to y. We multiply it by x equals minus 4. Okay, distribution time. Minus x squared minus 2x equals minus 4. All right. Let's bring everything to one side. Here's what I'm going to do. I'm mentally going to swim these two over here so they become positive, and then I'm going to rewrite it in the opposite order. So I'll have positive x squared plus 2x minus 4 equals 0. Okay, just swimming those things around quickly. All right, we are ready to drag out the dragon, aren't we? X equals minus b plus or minus the square root of. Please make sure you have this memorized really, really well. There it is. Our a equals b equals c equals, okay, a equals 1, b equals 2, c equals minus 4. Set up my buckets. A is 1, B is 2, C is minus 4. Okay, this, I always solve what's inside of the radical first. It's 4 plus 16, which equals 20. So I'm going to go to the top of the next page and I'm going to write minus 2 plus or minus square root of 20 over 2. That will be this simplified. Okay, it's really tempting to think I could cancel some 2's there, but I can't yet. However, what I can do is break this down. It's 4 times 5. 4 is 2 times 2, and then there's the 5. So I can pull out a pair of 2 pigs and bring them out here as a single 2, and that will leave me with a 5 inside. So that gives me x equals minus 2 times the square root of 5 all over 2. Now, I was just having this conversation with a student earlier this week. At this point, technically, you cannot cancel because you're subtracting these two guys. If you're adding or subtracting, you can't cancel. However, what we can do is factor. We can factor in the numerator. So we'll say x equals, now we'll pull a 2 out of both of these terms. So that will leave us with a minus 1 and then a minus square root of 5. That's over 2, right? We factored the 2 out of this. We can double check it by distributing it back. We would get minus 2 minus 2 square root of 5. And that's exactly where we started. So we know we factored it right. Now we can cancel because this 2 is not being added or subtracted. It's only being multiplied by this. But now we can cancel. And so we get x equals minus 1 minus... oh, I dropped my plus or minus. There it is. I was going to say I'm supposed to have 2 values here. Okay, so that's what we need to split, right? Into the 2 sides and carry on. I'm going to go to the top of the next page. Minus 1. And I'm going to split it into the 2 columns at the top of the next page, right? I'll write the plus and then I'll write the minus. Okay, now I have to go back and pick one of my equations that I think would be the easier one to substitute into. I don't want to divide, I want to use this one. It's all set up for me, right? Y equals minus x minus 2. Okay, so for this side, y equals minus x minus 2. This becomes a positive 1. Y equals 1 minus the square root of 5 minus 2. So y equals 1 minus 2 is minus 1 minus the square root of 5. I feel like I'm talking in circles at this point, right? But you can see how I simplified there. Those two go together to make a positive. 1 minus 2 is minus 1. Okay, so now I have a pair of points here. My x value is that, and my y value is, oh, that's very confusing, isn't it? Okay, now we'll go over and do the second one. Again, we're substituting this into this and simplifying for y. Y equals minus this minus 2. Distribute this minus sign across. And then combine the 1 and the minus 2. And now we can write our second pair of points. And usually with these problems, you'll know if you did it right because these same numbers, you should have all 4 versions with it being minus, minus. Never mind. Don't pay attention to what I was saying. It didn't come out right. But minus 1 plus square root of 5, minus 1 minus square root of 5. Minus 1 minus square root of 5, minus 1 plus square root of 5. That's correct. What I was saying was true for examples that have circles, but this one doesn't have a circle, so never mind. All right, that is a quick summary of nonlinear factoring. Now we're going to talk about factoring exponential expressions. This isn't super hard, but it's a little tricky. Let's begin with a review of our rules for exponents. Okay, so the topic is factoring exponentials, but we want to just quickly review our rules for exponents. Hopefully I've beaten this so far into your brain that you could just summarize it all without me saying a single word. I'm going to assume that's not necessarily true though, and I'll help. Rules for exponents. The first rule is called the product rule. And it says that if we're multiplying two bases that match and they each have an exponent, we can just add those exponents together. Right? The next one's called the quotient rule. Quotient, that sounds like division, doesn't it? And that's what it is. If we're dividing two bases that match and they each have an exponent, we can simplify by subtracting. Subtract bottom from top. All right, and then we have one called the power rule. And that's what we use when we have a base and it's been raised to an exponent and then we're trying to raise it to an even higher exponent. We multiply. Okay? These rules are going to be at play in this next section because we're going to be talking about exponents. All right. Example 19.4. Factor. helps in these problems is if we break this down and write it out the long way before we try to simplify it. All right, so this thing, what this really represents, this whole big chunk, is we have 3 and we're multiplying it by x to the n times x to the n times x squared. Right? We added these together because that's what our rule for exponent says. If you have matching bases, then you would add them. So we would have n plus 2. And yeah, that makes sense because we would rewrite that as just 2n plus 2. So this is what the original factors look like before we wrote them that way. This, we can break down a little more. It would be 3 times 4 times x to the n times x to the n times x to the n times x to the third, right? 3n plus 3. And you know, this we could even break down further. This could be x times x, right? Because x squared that we added there, we could break that down this way. And this we could break down as x times x times x. So if our exponent has a number on it, we can break that down into the individual x's as well. Now, let's take a different color and let's circle the common factors. And I could have broken this further down, but I knew that just taking out the common factor of 3 is what I was really going for, right? So they each have a 3. They each have an x to the n. They each have a second x to the n. Now this one's got one more, but I've run out of x to the n's over here, so no more. I'm finding the greatest common factor, right? Greatest common factor. So I'm done with the x to the n's. Now in these plain x's, there are 2 that they share. So our greatest common factor, whoops, is 3 x to the n, x to the n, x, x. And we can summarize this as 3x, remember these are 1s, right? We can add these all up. N plus n would be 2n plus 2. So that's our greatest common factor. And then what would be left? Let's see, in this first term, we used up everything, didn't we? All of these pieces all made it into the greatest common factor. So that would just be a 1. And then what's left over here? It would be plus 4 times x to the n plus 1. There's the n and there's the 1, and we add them because when you're multiplying the bases, you add the exponents. So this is our final answer. I wrote the greatest common factor in a different color so you can kind of follow the logic of that. 3x to the 2n plus 2 times the quantity 1 plus, yes, just double checking to make sure I'm right. All right, let's try one more of these. I'm going to go to the next page so I have plenty of room. I'm just flying through this book. Example 19.5. And let's see what we've got. Okay, this looks like a lot, doesn't it? Hard to know what to do with this. When I see the 2 parts together though, that tells me I bet I multiplied those together. So I could unmultiply them, right? Reversing the power rule. This could be x squared raised to the a power, or it could be x to the a power squared, right? I don't know which of those was powered before the other. I could write it either way. Similarly, with this one, I could write this either way. This could either be y squared raised to the b power, or it could be y to the b power squared, right? Now, I'm kind of interested in this one because it makes them match a little bit more. And I can rewrite my denominator to say x to the a squared minus y to the b power squared. And this puts me in mind of a difference of two squares, because that's equal to a plus b quantity, a minus b. Doesn't matter which is first, the plus or the minus. Remember this little guy? This is in that form. So that means I could write this, and we're still in the numerator, remember, we still have the denominator to look at. It could be x to the a plus y to the b times x to the a minus y to the b. That's me taking this expression and using this shape to factor it. So now I have all of this, right? This is my reshaped numerator. Let's put it over my denominator and look at what happy thing happens. Cancels out part of the numerator. So our final answer is x to the a minus y to the b. That's it. Oh, what joy can unfold when we factor exponential expressions. It's kind of tricky when you first look at it, but when you remember to use your rules for exponents and you see how we can break it down and make sense of it, I think it becomes a lot more manageable. Let me know if those give you any drama. I'm moving on to our last section. We have two more problems, but this is very straightforward. It's the sum and difference of two cubes. And it's cute because John just helped us to review the difference of two squares, right? If we're subtracting one square from another perfect square, we can factor them like so. And as I always like to say, it doesn't matter if the plus is first or second, as long as we have one minus and one plus. This is the difference of two squares, right? But there's also a pattern for the sum and the difference of two cubes. So let me remind you of those. And these we just memorize. Oops, that's a B. Copy, and then I'll give you a few tips on how to memorize. Okay, the difference of two squares is here just to remind you that that exists. These are the sum and the difference of two cubes because they're to the third power. Here's something I want you to notice. If there's a minus between the cubes, there's also a minus between the first degree terms in the binomial, right? Minus, minus, plus, plus. Then the trinomial that comes after is exactly the same for the two of them, right? A squared, AB, B squared. But look what happens with the signs. In the minus, this sign is a plus. in the plus, this sign is a minus. The second sign in the trinomial is always positive. So there's a pattern to this that makes it reasonably easy to memorize, and I do want you to memorize this.